Hi there. This is the first module in the heap exploitation course, and it's probably the most important one. It is Intro to glibc Malloc. So we're talking about Malloc from afar. Why do we need it? What is it even for in the first place? So the stack tends to be static or stactic. Gotta love a good joke. Meaning it doesn't change in size. So if you know something is size 10 at compile time, then you can use that. The other thing is that it doesn't have a particular scope. That's nice. If you use something like alloca, when you're programming in C, then you run into issues with scope. And although it's a lesser common vulnerability, if you use a pointer to the stack while in a frame that's been destroyed, then you have a use after scope vulnerability. And the nice thing about the heap is that the heap is global. In particular, it is a per process piece of memory. And that's really helpful because I can send it between threads, or I can get some data, or I can allocate some data on the heap and return it, and that's fine. The stack also has much lower size limits. So there's a time for the stack, there's a time for the heap. So the heap is good. But why do we use Malloc in particular? Why is Malloc so special? See, back in the day, you would either use BRK or SBRK, which is set break, in order to change the program break. And this defines the process's data segment. And you could just move it back and forth. You could also use mmap, theoretically, to map your own memory as well in a kind of a similar way. But there's no way to easily reuse it. The problem is that I would allocate something that I wouldn't need anymore, but I can't reuse that data. Because it's terribly inefficient, we're gonna fix that inefficiency. And that inefficiency fix was writing an allocator. An allocator will allocate as little memory as possible, and then it manages memory no longer being used. And it will then give that memory out once it's no longer being used. The two main functions you have to worry about are malloc, which allocates data and gives you a pointer to some amount of space. And then there's free. Free is going to store that data that's no longer being used, and it's assumed that you are no longer using that as the developer. And everything else is just magically abstracted away for you. There's lots of different allocators. DL malloc, glibc is what that turned into. TC malloc, G malloc. So why are we so specialized on this one? This is the most basic one, and it's used on most Linux distros, meaning that it's used in a lot of IoT devices as well. A modified older version of libc called ulibc is also used quite a bit, although I was looking at a device recently, and it was just using glibc 2.31, which came out like 3-4 years ago, something now. Anyway, exploiting heap memory corruption vulnerabilities is specific to the heap implementation, which is why knowing the internals is so important, although the bug classes between them are universal. And just make it clear, the focus of this course is glibc malloc heap exploitation. So now we're going to talk about the basics of the allocator. We're going to talk about data structures and chunks. We're going to have an exercise break, then we're going to talk about bins and ordering, and then another exercise break. So this broken up into a few different videos. So a lot of you guys are familiar with basic data structures, but it's always good to go through them again. It's good to see. So a linked list is a collection of data where you have a data and then you have a pointer to the next object in that data. This is really nice because unlike an array, which has to be continuous in memory, linked lists don't. You can have as many or as few elements as you would like. And at the end, you set the next pointer to be null. This is a pretty fundamental data structure. You'll see this within the Linux kernel and a lot of C-based programs as well. There's also a doubly linked list. The main difference is that a doubly linked list can go backwards and forwards. So with a singly linked list, you could start from the head which is the beginning of the list, and go all the way to the end. With the doubly linked list, you can start from any node and go to any other node. So I could start from the middle one and go to the front or the back. And you do this using the pointers in the linked list. Again, advantage is that it doesn't have to be contiguous in memory, or consistent all the way through like an array. Although my video is covering up part of it, hopefully you can still see that okay. There are two pointers that are special, though, that we'll see quite a bit. The first one is the head. The head is a pointer to the beginning of the linked list, and a tail is the last member of the list. In particular, it's a pointer to it. It's really nice to have these because you need to know where the list starts and be able to traverse through it. That's the only data structure you really need to know. It's nice to have some background in assembly and binary exploitation, because this is more of an advanced binary exploitation topic for sure. So I'm going to talk about chunks in this video, and we'll talk about bins and arenas in a different video. So chunks are the basic piece of memory that comes back from a call to Malloc. When you call Malloc and say, hey, I need 10 bytes, or whatever you need, this is what actually gets passed back to the user. A heap is made up of many chunks in practice. However, it starts off as just one big slab, effectively. The data structure for a chunk has 4 main fields. It has 2 more, but we'll talk about that later. The first and most important one is the size. This is the physical size of the chunk in memory that you've been allocated. And it doesn't necessarily correspond to what you asked for either. We'll talk about that in the next video. So here we can see we have a chunk of size hex 90, hex 100, and these are all because they were asked by the user to have something of that size. Now the size isn't just the actual size of it, the chunk. The final 4 bits are unused because things are 16-byte aligned on 64-bit and 8-byte aligned on 32-bit. So these final 3 bits actually have some special meaning to them. The main one that we want to care about right now is the P bit. The P bit stands for prev in use. And all this is really weird to visualize. I hope the diagram on that side makes this nice to see. So this is asking, is the previous chunk to me in use? And if this is a 0, then it is not in use. If it is 1, then it is in use. So practically speaking, if you're on the chunk on the top, we're calling the current chunk, it goes, am I allocated or not? I'm not sure. So it goes ahead of it. And you can do this using the actual size and removing the metadata bits. And then it goes forwards in order to find it. Once it finds the size of the chunk ahead of it, it then can check if it's 0 or 1. If it's 0, it is not in use, and it's free at that point. And if it's a 1, then it means it is in use. So this is, if you're looking at the Malloc source code, this is actually how it works for figuring out if the chunk is free or not. The prev size is a way to go backwards in memory. Just before we use the size to go ahead in memory. So this is offset 0. All of these fields are 8 bytes in length. I forgot to mention that before, at least on 64-bit, which is what the course is in. It should be noted, though, that this is only in use when the prev in use bit of a chunk is not set, meaning that the bit is 0. This is because otherwise the prev size field is actually used by the data of the previous chunk. But when the chunk is free, there's no reason for it to need that. So it uses this. Back in the day when this allocator was written, in like the early 90s, size is really important. So 8 bytes or 4 bytes would have been 32-bit at the time was actually really important. So to use prev in use, if we have current chunk at the top, or it's the bottom of the page and previous chunk at the top, and we want to go backwards and find the chunk, we would use the prev size to know how far backwards we need to go. So we just take the pointer of the chunk, subtract it by the amount of the previous size, and we would hit it. The final two fields are linked list pointers, like we talked about before. If you remember where you get that PhD in linked list, this is what we were doing it for. The FD and BK are the next and pre from our previous example. The FD stands for forward and BK stands for backwards. So we're going to talk about bins in another video, but know that we need a way for the bins to track the chunks. So the bins are effectively just pointers to the chunks. In particular, like they're just head and tail pointers if it's a doubly linked list. So otherwise, we need to know how to traverse between the different chunks or the elements in the linked list. So the FD and BK fields are what is used to do that. If it's a singly linked list, then it uses only FD. If it's a doubly linked list, then it uses FD and BK. You'll notice that there's a big, thick line here as well. This is a big, big thing. So in this slide, I say it's only used when the chunk is free. That's really important. So that big, thick line is where the allocation is actually going to. So the size of the chunk, the prev size and size, is not something that the user gets to modify. And that makes sense. That's a vulnerability if you could do that. But the FD and BK are within the data of the chunk, but they're only used when the chunk is free. So what the user actually gets back to them when they call Malloc is a pointer to where this thick line's at after the prev size and size. So it's an offset of hex 10. I think this diagram is really helpful. It's really hard to visualize the difference between FD and BK and the size. So the size is the actual size of the contiguous chunk in memory. Notice that here, the size represents this entire red arrow. So it's going ahead of this chunk in actual memory. While the FD and BK have nothing to do with the actual size, they're just linked lists. And as we talked about before, linked lists don't have to be contiguous. It's just a pointer to the next freed chunk. And that's what these black arrows are representing. And these green, and coming from here, this green box is effectively a bin or a pointer to these linked lists. So the size is the physical size of a block of memory. The FD and BK is a pointer to the next chunk in linked list or the previous chunk. So normally when I did this in person for all these conferences, we just waited a minute, but this is a video, so we'll just pause. So I'm going to ask all these questions. I want you to pause the video and think about them. Just to prove comprehension. What is the previous size used for? What is the size used for? What are the FD and BK used for? If you guys watch a Gad Master, it's a chess guy. This is where he pauses, looks around the room a little bit, and then goes, and congratulations if you picked the next correct move of D5. Whatever. It's funny. So, the prev size is used for finding the previous chunk. The size is used for the size of the current chunk in the metadata, and the FD and BK are used for the forward and back pointers in the linked list. Although these are simple and I just talked about them, it's good to have this cue of, oh, I learned that, I understand this now. There's one more chunk that I think is worth talking about, and this is the top chunk. If you remember what I talked about before, where there's this really large SBRK allocation at the beginning, well, we have to keep track of the size of that allocation. And that's what the top chunk does. The top chunk holds the size of the total amount of memory left from the SBRK allocation. It's always at the very top of the heap segment as well. It doesn't use the prev size FD and BK because it doesn't need to. The top chunk is at the top of this. So here, while at the start of the heap, we'll have some chunks that are in use, and we have the top chunk. And this size here represents, oh, there we go. This size here represents the rest of this area. And when you need the heap initially and it does its allocation, it will be most of the entire segment. Cool. So to recap, the prev size is the size of the chunk below and only use if the previous chunk is free. The size is the size of the chunk plus metadata. The FD is the next chunk in the linked list, and the BK is the previous size of the chunk. But these are BK is a previous chunk in the linked list as well. And then these are only used when a chunk is free. Very particular about that. It's really important to understand. So that leads us into the exercise. I will stop here. Thanks for listening.